This video subject matter covers the course Pre-Calculus and more specifically a unit in trigonometry. And within that unit, the lesson that we will be talking about is the 6 trig functions. So here are some learning objectives here that we will be addressing throughout this lesson. The first being to compute the values of trig functions for key angles. The second being prove trigonometric identities, and the third being solve right and oblique triangles. Now, we may not be hitting these exact objectives in this lesson, but the objectives that we will be covering in this lesson down here will help us with these student learning objectives. So in this video, we're going to talk about the 6 trigonometric functions and reciprocal identities. We'll talk about quadrant signs of each trig function. We will find the values of the 6 trigonometric functions given a triangle, a specific trigonometric value with a given quadrant or a point. And lastly, we will talk about the tangent ratio identities and the Pythagorean trig identities. And we will start baby trigonometric identity verification. On this slide, we will talk about the 6 trigonometric functions. And when you first learn about these functions, you normally just learn about sine, cosine, and tangent, maybe back in geometry in high school. And these 3 trigonometric functions are easiest to explain using a triangle. So you can see here we have this symbol inside these trig functions, and that matches up with this symbol here. Theta, or any other Greek letter, is what we use in math to represent the measure of an angle. And so since we know the angle is down here, the angle will always be made up of the 2 sides of the triangle being the hypotenuse and the adjacent side. The side that is across from the angle over here, we will call the opposite. So we say the sine of an angle just ends up being the ratio of the opposite side to the hypotenuse. So there we have it here, opposite over hypotenuse. The cosine of a given angle ends up being the ratio of the adjacent side divided by the hypotenuse. And the tangent of an angle is the ratio of the opposite side over the adjacent side. But in pre-calculus, we learn about these other 3 trig functions down here. Now these are called cosecant, secant, and cotangent. And these 3 particular trigonometric functions are just defined using, again, hypotenuse, opposite, and adjacent, like this. The cosecant of an angle is the hypotenuse over the opposite side. The secant of an angle is the hypotenuse over the adjacent side. And the cotangent of an angle is the adjacent side over the opposite side. And you might notice something over here on the right side of the screen, being that the sine of theta is opposite over hypotenuse. Well, if we just reciprocate this fraction, we end up getting the cosecant of theta. So sine and cosecant are reciprocals of each other. The same thing with cosine and secant. Those trigonometric functions are reciprocals of each other. And tangent and cotangent are also reciprocals of each other. Here's opposite over adjacent, down here adjacent over opposite. And this leads us over into the reciprocal identities. Here on this slide, we will write the 6 reciprocal identities for these trig functions. I just made mention on the previous slide that sine and cosecant are reciprocal identities. So this is how we will write this. Sine of theta is the same thing as 1 over cosecant theta. And cosecant is the same thing as 1 over sine theta. For the next two, I mentioned on the last slide that cosine and secant are reciprocals of each other, so we will write it like this. That cosine is 1 over secant theta, and secant is 1 over cosine theta. And lastly, with these last bottom two down here, tangent and cotangent, you're probably seeing a pattern. 1 over cotangent theta is the same as tangent theta, and 1 over tangent theta is the same thing as cotangent theta. So these are helpful. You'll see in the next few slides and some examples when you're asked to find all 6, the values of all 6 trigonometric functions given some information. Or it is also very handy to know these when we start verifying trigonometric identities. Let's take a look at the former. Find the values of all 6 trigonometric functions for the given angle. Now here in this picture, we have a right triangle, and the angle is clearly labeled. So we already know that the hypotenuse and the adjacent side are the legs of the triangle that form the angle. So this side will be the hypotenuse and this side will be the adjacent. Which means this other side over here, this 15, this is the opposite side. So now we can find all 6 trigonometric functions of this angle. Now, if you can remember back a couple slides, that sine of theta is just the opposite over the hypotenuse. So this means that sine of theta is just 15 over 17. Right? That's how long the opposite side is divided by how long the hypotenuse is. And we can do this for cosine with adjacent over hypotenuse and get 8 over 17 as the adjacent side is length 8 and the hypotenuse is length 17. And we can also do this for the tangent of theta, and that is the opposite over the adjacent. So the measure of tangent of theta for this triangle would be 15 over 8. Now you could go through and do cosecant, secant, and cotangent, just like you saw the definitions of those a few slides ago, where cosecant is the hypotenuse over the opposite, or you could start remembering that sine and cosecant are reciprocals of each other. So if you already know that sine is 15 over 17 and you're trying to find cosecant, that means cosecant will just be the reciprocal of 15 over 17, which will give you 17 over 15. And the same can be done for cosine and secant. You can just take the reciprocal of cosine and you will get secant, which is 17 over 8. And lastly, with cotangent, cotangent is the reciprocal of tangent, and that would give you something like, 8 over 15. Now, one thing you want to keep in mind as you're going through and doing these is if you can reduce the fraction, please do that. That will make life a lot easier later on. Find the values of all 6 trigonometric functions for the given angle. So here again, you can see that there is a triangle. In fact, it's a right triangle. Here's a 90-degree angle. And we're asked to find sine, cosine, tangent, cosecant, secant, and cotangent of this angle. So let's do a little bit of labeling here. I know that always this angle is made up by the two sides that would be the hypotenuse and the adjacent side. So I'm just going to label that really quick, the hypotenuse and the adjacent. But the opposite side here has no value. It's not given anyway, but you can find it using the Pythagorean theorem. And so I'm going to call this opposite side A. That means 1 over here would be B, and the hypotenuse will be C. So when I use the Pythagorean theorem, a squared plus b squared equals c squared, I can substitute some numbers in there. So I don't know A. I do know B plus 1 squared equals 3 squared. I can go ahead and find what A is equal to. So this is a squared plus 1 equals 9. A squared equals 8. And A equals 2 square root of 2. So this is what A is equal to as long as you see that you can take the square root of both sides and you reject the negative answer, because the negative answer cannot accurately describe a distance. Also, the simplification of 8 to 2 square root of 2 will help out later on. All right, so now that we know that this opposite side is 2 square root of 2, we can start filling in these trigonometric functions. And I'm going to give you about 5 seconds to pause the video after I stop talking so you can try filling these in for yourself. So here are the answers for these, and hopefully you got something like this. But there is one little thing that we need to take care of, and that is these square root of 2's in the denominator. This is going to be your first taste into rationalizing a denominator. And essentially all that means is that we don't like having square roots in the denominator. So in order to get rid of the square root in the denominator, you will multiply the top and bottom by whatever is inside the square root. So multiply top and bottom by square root of 2 for each fraction. And what that does is that now the square root of 2 times the square root of 2 in the denominator becomes a 2. So these two multiplied together becomes a 2. 2 times this 2 gives me a 4 in the denominator. And in the top, I just have 3 square root of 2. And the same thing will happen down here. The square roots of 2 will multiply together to give you a 2. Times 2 is 4. And in the top, I have 1 times square root of 2 is just square root of 2. Find the values of all 6 trigonometric functions for the given angle theta. And this is even different yet from the previous 2 examples. I mean, the previous 2 examples weren't too different from each other. The second triangle only had a side missing, and that was the only difference, and maybe a little bit of rationalization. With this one, there is no triangle. So let's draw one. If you don't have a triangle, let's draw one. So here's my triangle. And now what am I supposed to do with this? Well, I know I have a right angle here, and I want to put my theta right here. Why not? So I know, I'm just going to start labeling. I know that this will be my hypotenuse and this will be my adjacent. Just because the hypotenuse and the adjacent side always make up the angle. And whatever's the third side will be considered the opposite. Now there are no values here. I mean, we just have a triangle that's labeled hypotenuse, adjacent, opposite with an angle theta. How are we supposed to fill this in? Well, the answer is right here. We have a cotangent that is equal to 7 over 24. Now, remembering back how you find cotangent, you would take the ratio of the adjacent side over the opposite side. So now we have values for the adjacent side being 7. So I'm going to set adjacent equal to 7. And the opposite side equaling 24. Now, mind you, my drawing is not to scale, and that's fine. As long as you go through and you label each side, the value of each side, you're going to be just fine. So now we're back in a situation like we had in the last slide, where this and this side, we know A and B, we don't know C, so we have to use Pythagorean theorem, which looks something like this. All right, so I chose this to be A and this to be B. Simplified it all down, square root both sides. The hypotenuse here is length 25. So you can go through and figure out all 6 trig functions as such. So you can try to piece this together for yourself. You've seen a couple examples of how to do this already. Couple things to keep in mind when you're going through and doing these. You may not be given a triangle at all. You can create one, given some information that you're given. You might end up with square roots in your answer, and that's fine. And when that happens, you will need to rationalize your denominator and just start memorizing. The adjacent over the hypotenuse is what makes up a cosine. The ratio of the hypotenuse over the opposite is what makes up cosecant. Or that cosecant is the reciprocal of sine, or that cotangent is the reciprocal of tangent. There's a lot going on here, and you will have lots of practice with this. Find the exact value of the 6 trigonometric functions for the following angles. So here, you can see that there are 2 angles, 180 degrees and 5 pi over 2 radians. And to better understand how to find these angles, or how to find the sine, cosine, tangent, and all of those like this, is to first remember that 180 degrees is over here to the left side. So if this is the y-axis and this is the x-axis, it is the negative x-axis. So what you can think of it like this. I'm going to put a very little triangle here. Now mind you, 180 degrees is on the x-axis, but I'm putting this little triangle here to give a little bit of representation about what's happening. So there's this little angle formed by the, let's see if I can do this here, formed by this side and formed by this other side up here. And that is where theta is. Theta is between this and this, the x-axis. So it doesn't matter how long this side is. those two sides will be the same length. So let's just call it 1. Let's make it something easy. 1, 1. And this is the adjacent, and this is the hypotenuse. And right over here, this short edge, that one technically is 0. I'm just giving a little bit of height there so you can see where everything is going. And this is the opposite side. So here we can see a few things like the opposite over the hypotenuse is the sine of theta. So that's 0 over 1, which is just 0. Let's see, what else do we have here? We have cosine is adjacent over hypotenuse, which is 1 over 1, which is just 1. And tangent of theta is opposite over adjacent. So 0 over 1 is 0. Now, funny things start happening when you look at the reciprocals of these fractions. So for example, if you look at the cosecant of theta, and I'm just going to reciprocate this fraction right here. So that is 1 over 0. So 1 over 0 is undefined, and so we write undefined. So the cosecant is undefined at 180 degrees. But secant's fine. So you can see 1 over 1 is still 1. So secant is still 1, but tangent, on the other hand, is just like what happened with sine. When you take the reciprocal of 0 over 1, cotangent becomes 1 over 0, which is also undefined. So here we have these 6 trig functions, the values of the 6 trig functions for this 180 degree angle. And something very similar can be done over here with the 5 pi over 2. Let me get some axes drawn here. There we go. And 5 pi over 2 means we will start at the positive x-axis. There's 1 pi, there's 2 pi, and if this whole distance here from the positive x to the negative x-axis is 1 whole pi, half a pi would stop right here. So that means we would stop right here, which means that the angle would come out from the origin. Get a bit of erasing here just to make sure. So the angle should be straight up and down, and I'm angling it just a little bit so you can see what's going on here. But we always draw back to the x-axis. So really, this side right here is 0. And if I had to call these other two lengths some distance, I would call them each 1. So now the theta is right here, meaning this is adjacent, this is opposite, and this is the hypotenuse. So you can find the other values for the 6 trig functions for this one almost exactly the same way as over here. And when you do that, you'll end up with values that look like this. And there you have it. And that is because values can start taking on negatives. So for example, we know what the adjacent side is. It is negative 8. So this is negative 8. The opposite side is now negative 15. The hypotenuse, we have to figure that one out. We don't know what that is, so let's take a very quick Pythagorean identity here, which would be negative 8 squared. I'll call that A, and plus negative 15 squared equals c squared. C is always the hypotenuse. So this gives me 64 plus 225 equals c squared. This is equal to 289 equals c squared, which means c equals 17. And make no mistake, this is a positive 17. So the hypotenuse is a positive 17. So now our opposite and adjacent sides have negative signs, and the hypotenuse is still positive. So when we find these 6 trigonometric functions here, the sine of theta is the opposite, negative 15 over the hypotenuse, 17. The cosine of theta here is the adjacent, which is negative 8 over 17. And the tangent, something fun happens here, ends up being negative 15 over negative 8, which is just 15 over 8. So if you wanted to find the other 3 trig functions here for this particular point, you would need to just reciprocate these 3 trig identities. And so here's what these 3 trig identities look like. So I'm going to, again, give you a few seconds to try this one here. So you'll make sure you put this in the correct place and see if you can find all 6 trig values. So here's how this entire one is worked out. The point negative 2, 3, the adjacent side is negative 2, the opposite side is 3, and by Pythagorean theorem, the hypotenuse is the square root of 13. So I can go through and do opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, find the reciprocal of all these, and I'd be done, except in the denominator again here, there's a square root of 13. So you would need to multiply top and bottom of this fraction by square root of 13 to rationalize the denominator. And that just gets the square root out of the denominator. So square root of 13 times another square root of 13 would be 13. 3 times square root of 13 is 3 square root of 13. And you can use the same logic over here with this particular rationalization. Now, I urge you to write all of this stuff down for what is going over on the next slide. Like, we're going to start looking at the signs of different trig functions depending upon where these points land in the coordinate system. So go ahead and write these down, and I'll continue to the next slide. On this slide, we're actually going to talk about the quadrant signs for the different trig functions. And you may have heard before, maybe you haven't, hopefully you'll understand when this is done, that over here, if this is the y-axis and this is the x-axis, the first quadrant was the upper left quadrant, or the upper left portion between the positive y and the positive x-axis. Quadrant 2 is the upper left portion here between the positive y and the negative x-axis. Quadrant 3 is down here between the negative x and the negative y-axis. And quadrant 4 is between the positive x and the negative y-axis down here in the lower right. And you can see here also that I've labeled a few angles, like the positive y-axis is 90 degrees or pi over 2 radians. The negative x-axis is 180 degrees or pi radians, and so on and so forth all the way around the axes. So what I want to talk about here is that if you end up having a point that lands in the first quadrant, all values of all 6 trigonometric functions will be positive. So I'm going to write over here in quadrant 1, all values are positive. And that's sine, cosine, tangent, secant, cosecant, cotangent. All 6 trig functions will have positive values if that ordered pair is in the first quadrant. Now it starts changing as we start moving around the quadrants, and you can see we're moving in a counterclockwise motion here. Over here in quadrant 2, it's going to be sine values are positive. In quadrant 3, it will be tangent values are positive. And in quadrant 4, it will be cosine values are positive. So one way you can remember this is that all in quadrant 1, so A, sine in quadrant 2, S, tangent in quadrant 3, T, and cosine in quadrant 4, C. And since we're moving around in this counterclockwise motion, you can use this with, use an acronym to help you think or remember what order this goes in. But a pretty standard one is all students take calculus. All students take calculus. There are many others. Find one that works for you so you can remember that. But before we move on and actually apply these different quadrant signs into actual exercises, I need to mention that all values are positive. I mentioned all 6 trig functions here: sine, cosine, tangent, cosecant, secant, cotangent. But over here, it's not just the sine values that are positive, it will also be the cosecant values as well. And that's because the cosecant is the reciprocal of the sine function. So you may guess that in these other 2 quadrants down here, 3 and 4, there are also some extra functions that will also be positive. So down here in quadrant 3, it's not just tangent, but also cotangent. In quadrant 4, it's not just cosine, it's also secant that will be positive. So what does that mean for the rest of them? You see here in quadrant 2, sine and cosecant are positive. Well, that means every other trig function will take on a negative value in this quadrant. And if you go back and look at what you wrote down from the last slide, when we had the point 2, -3, or -2, 3, so here's -2, here's 3, and we had this line drawn, and we were trying to figure out all of the 6 trig functions here. The sine and the cosecant were the only positive values. The cosine, secant, tangent, and cotangent were all negative. And the same thing happens when we were looking over here at -8, -15, this point down here. For the first example on the last slide, there was this theta here. The tangent and cotangent values for the first example on the last slide were only once positive. Sine, cosine, secant, cosecant were all negative. So when we start looking at trig values within a coordinate system, you start getting positive and negative answers. Find the quadrants containing theta if the given conditions are true. So all we're reporting back for these three examples is some quadrant number. So how you can think of this is, you can see in the first example over here in quadrant part A, that the tangent is less than 0, and if you're less than 0, that means you're negative, and that the cosine is bigger than 0, and if you're bigger than 0, that means you're positive. So I know that cosine is positive. I like to start with the positive ones first. Cosine is positive in quadrant 4 and quadrant 1. Everything's positive in quadrant 1, but cosine and secant, its reciprocal, are positive in quadrant 4. So it's got to be one of these two. Let's see if we can narrow it down with this other piece of information here. Tangent is negative. Well, everything is positive in quadrant 1, so cosine is positive and tangent is positive, but we're looking for where tangent is negative, so that must mean it is quadrant 4. So again, in quadrant 4, cosine and secant are positive and everything else is negative. So tangent is one of those everything else, so it must be quadrant 4. In the next example, we have the cosecant is bigger than 0, so that's positive, and the cotangent is less than 0, that's negative. But we don't have cotangent and cosecant listed over here anywhere. We have all sine, tangent, and cosine. So when you have these other trig functions like cotangent, cosecant, or secant, you can rewrite these with the reciprocal identity. So if the cosecant is positive, that's like saying that the sine is positive. And if cotangent is negative, that's like saying tangent of theta is negative. So we can get the same answer if we look at where sine is positive and where tangent is negative. And we already know that quadrant 1 and 2 is where sine is positive, but everything is positive in quadrant 1, which knocks that one out because we want the tangent to be negative. So the answer for part B would be quadrant 2. The sine is positive and everything else is negative, or the sine and cosecant are positive and everything else is negative, including cotangent. So this will be quadrant 2. And in the last example, you see here we have a cosine of theta is less than 0, so that's negative, and a cosecant is less than 0, that's negative. But we don't have a cosecant, so you saw it over here. We can write that as a sine of theta. So where is sine less than 0 and where is cosine less than 0? Well, it can't be quadrant 2 because sine is positive. That takes care of that one. That one's no good. It can't be quadrant 1 because everything's positive and both of these are negative. It can't be quadrant 4 because cosine is also positive here. So it must be quadrant 3. Tangent and cotangent are positive here. Every other trig function is negative. So for this last example, quadrant 3. The last part of this lesson involves other identities involving trigonometric functions, such as tangent ratios, and that is the tangent of theta is equal to sine of theta over cosine of theta, And the other tangent ratio involves the cotangent of theta, and that is the cosine of theta over the sine of theta. And so I want to prove these really quickly, or prove one of them really quickly, just so you can see. If we break it down into the sides of the triangle here, that the sine of theta here over the cosine of theta here would be the opposite over the hypotenuse, all divided by the adjacent over the hypotenuse. And since we have fractions that are within fractions, we can multiply by the LCD here, which is the hypotenuse, and that'll reduce all of those, leaving you with opposite over adjacent, which is exactly equal to how you find the tangent of theta. So the sine over cosine is equal to the tangent of theta. And you can do something very similar for cotangent. You can start with cosine over sine and change it over to opposite over hypotenuse or whatever, and then simplify, and you'll end up with cotangent over here. So these work. These are tangent ratios, and again, these ratios right here are going to be good for verifying trigonometric identities, which we will get into in the next few slides. And then finally down here we have what are called the Pythagorean identities, and you can see that there are three of them. And the first one is sine squared of theta plus cosine squared of theta equals 1. 1 plus cotangent squared theta equals cosecant squared theta, and tangent squared theta plus 1 equals secant squared theta. So again, we can prove this just by going back to what it means to be a sine and what it means to be a cosine back with the triangle. And this is actually going to be your first little proof, if you will, on how verifying trigonometric identities works. In fact, it was up here. This is your very first one, using the opposite and hypotenuse and adjacent sides of a triangle. So the sine of this triangle is the opposite over the hypotenuse. So let's see. This is opposite over hypotenuse, and it's going to be squared. The cosine is adjacent over hypotenuse, and that will be squared, and that equals 1. So I'm just going to work on the left side a little bit, and I'm going to see if I can manipulate this down to the other side of this equation being 1. So when I square everything here, I'm going to end up with, let's see, opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. And I can actually add these two fractions together because they have a common denominator. So let's see, I'll have opposite squared plus adjacent squared over hypotenuse squared. And this is where knowing your Pythagorean theorem comes into play. If you square the opposite side and you add it to the square of the adjacent side, that will give you the hypotenuse squared, right? A squared plus b squared equals c squared. So this entire thing here equals hypotenuse squared over hypotenuse squared, which is just 1. So again, this is a very simple little proof to explain why this works. You don't have to know how to prove these identities, but we're going to use these to prove bigger and better identities. So these tangent ratios and Pythagorean identities are super important for what's coming up in the next few slides. On this slide, we will use the previous page's worth of identities to help simplify some trigonometric expressions, as well as bringing in some older ideas such as factoring and canceling to simplify some other trigonometric expressions. So the first example that we have here is 7 secant squared alpha minus 7 tangent squared alpha. And I think I mentioned it one other time in this video that Greek letters get used for angle measurements. And so you can see alphas, you can see betas. I think you'll see a gamma coming up here, but most of the time you see this one down here, theta. But just be aware that they're just other letters or variables that we can use. So simplifying a trigonometric expression is similar to simplifying any other expression that we've looked at so far. And that is, if you notice that there is a common factor, you are going to want to common factor that out. So this will be 7 times secant squared alpha minus tangent squared alpha. And this should set off bells. I didn't say it in the last slide, but anytime you see two trigonometric functions being squared, such as secant and tangent, these are both being squared, you can do one of two things. You can try factoring this by difference of squares, but chances are there's an easier way to simplify this. So I'm going to come over here to the right side of the screen, and I'm going to write the Pythagorean identity involving secant squared and tangent squared. So you see here there is a Pythagorean identity involving tangent squared and secant squared. Now this isn't the exact way that this equation is written, but we can do a little bit of manipulation to this equation by subtracting tangent squared theta. And getting a new equation that looks like this, being 1 minus secant squared theta minus tangent squared theta. And as long as what's inside this set of parentheses matches, so theta, and here it's alpha and alpha, secant squared of something minus tangent squared of that same thing equals 1. Now, I don't know about y'all, but this is probably the strangest way I've ever seen the number 1 be written, but that's what this is equal to. Secant squared of an angle minus tangent squared of that same angle is 1, and that means our answer here is just 7. So while you're going through and simplifying trigonometric expressions, you'll want to take notice, are there two trigonometric expressions being squared? If so, is there a Pythagorean identity that relates those two? And you might have to manipulate the equation a little bit, but secant squared minus tangent squared is the same thing as 1. So that simplifies down really nicely. And the final answer is 7. So in this next example, with cotangent squared of beta minus 4 over cotangent squared of beta minus cotangent beta minus 6, these you will want to factor. You'll notice that it's just cotangent squared. There's no cosecant squared in any of this, which if you refer back to the Pythagorean identities, cotangent squared and cosecant squared are in the same equation. So since we don't see a cosecant squared here, you'll want to just see if you can factor this normally. So what do I mean by that? Just pretend like this is an x squared, and pretend like this is an x squared minus x minus 6, and then you can just go through and factor in the numerator by difference of squares. So cotangent of beta plus 2 times cotangent of beta minus 2, right? There's the difference of squares. And in the denominator, you'll have cotangent of beta minus 3 times cotangent of beta plus 2. And then you'll notice that this factor and this factor reduce, leaving you with a cotangent of beta minus 2 over a cotangent of beta minus 3 as the final answer. And this last one, write the tangent of theta in terms of only cosine of theta. Well, we already know by the tangent ratio identity that tangent of theta is the same thing as sine of theta over cosine of theta. So in the denominator, you're set. You already have cosine. But what this is telling you to do is to turn the numerator also into terms of cosines. So the question is, do you know an identity that relates sine and cosine? And yes, it's the Pythagorean identity. That is sine squared plus, let me be accurate here, sine squared theta plus cosine squared theta equals 1. So now, in order to get sine squared in terms of cosine squared, we need to solve this equation for just sine of theta. So that will require you subtracting cosine squared from both sides and then taking the square root to get rid of the square on the sine. So this looks like this. Sine of theta equals, what is it? The square root of 1 minus cosine squared theta. So this particular expression will get substituted in for the sine here. So you'll end up with a final answer of 1 minus cosine squared theta, a square root of all that over cosine of theta. On this slide and the next one, to end this video, we will be verifying trigonometric identities. And all that means is that you'll be given an equation, something like this or something like this down here. And you know that this left side equals this right side. This is true. This is a true statement. It may not look like it right now, but that's a true statement. And the same thing down here. This is a true statement. This left side equals this right side. How do we prove it? That's what the verification exercises get at. How do you prove that this side is equal to this side? Well, in order to verify inequality, what needs to happen is you need to start with one side of the equation and simplify it so that it'll look like the other side of the equation. And generally, the best way to do this is to start with the more complicated looking side. So for example, in this first example here, sine of theta times cotangent of theta looks a little more complicated than cosine of theta. And this is going to be easier to simplify anyway. So let's see what happens. Let's see, so sine of theta times cotangent of theta, well, there's nothing squared here, so I know I can't use any Pythagorean identities. Let's see, what else could I do here? I know that there's, changing sine using a reciprocal identity to cosecant, that's not going to help, or changing this to tangent, that's not going to help. I think the only thing we can do here is use the tangent ratio to rewrite this as sine of theta times cosine theta over sine theta. So this cotangent I changed into cosine over sine. Oh yes, so now it's all looking pretty clear now. So once you do this, it looks like the signs in the top and the bottom here can reduce away, leaving you with cosine of theta. So this work that is right here is the answer. so we rewrote cotangent as this ratio, canceled a couple signs, and got cosine. This is the answer that's on the other side of the equation. So that's it. That is the verification. All right, let's take a look at this next one. There we go. Okay, so we have tangent of theta plus cotangent of theta times tangent of theta equals secant squared theta. Now, again, I think this left side looks a little more complicated than this right side. Let's see, so secant squared theta, this lets me know maybe I'll be using a Pythagorean identity over here somewhere, because anytime I see that squared, I want to be on high alert for Pythagorean identities. So let's see what happens here. I guess the only thing we can do first over here is multiply tangent times tangent and tangent times cotangent. Let's see what that looks like. So that'll be tangent squared of theta plus cotangent theta times tangent theta. Now how does this help us? What can we do now? Well, I guess we could, let's see, we can't do anything with tangent squared, but that's good to know because tangent squared is here. And I know tangent squared and secant squared are part of the same Pythagorean identity. And here is that identity right over here. So tangent squared plus 1 equals secant squared. Oh man, we must be close here. Because we have a tangent squared. If we could change this to a 1 somehow, then we could get way down here something like tangent squared theta plus 1, which is the same thing as secant squared theta. It's just filling in these steps here. Let's see how we can do that. So tangent squared theta, I think we're just going to leave that alone. But I want to rewrite cotangent again, like we did here. Cotangent to be cosine theta over sine theta, and tangent as sine theta over cosine theta. So here cotangent simplifies to this and tangent simplifies to this. Oh yeah, check this out. So cosines cancel and the sines cancel and everything canceled, which gives us that 1. So again here, this is the work and your final answer to verify that this left side equals this right side. And over here we have a couple more verification exercises. In this first one, I see that I have the cosecant of gamma. This little symbol here is gamma. It's another Greek letter used to represent angles. Minus sine of gamma equals cotangent gamma times cosine gamma. What can we do here? Well, let's think. We have 2 terms on the left side, and we have 1 term on the right. I don't see any squares. What can we do here? Well, let's change 1 over cosecant gamma to 1 over sine gamma minus sine gamma. I think I like working with the side with multiple terms to begin with instead of 1 term. I think this is more complicated, and you can see that if you switch this using the reciprocal identity, yes, it becomes a little more complicated. So let's see where this takes us. So now that we have 2 terms still, one of them is a fraction now, we should combine these terms together to create 1 fraction. Let's see how we can do that. Well, I know I need a sine gamma down here, And if I divide by sine gamma, I can also multiply this term by sine gamma. And now that I have a common denominator, I can add these two things together. So it'll end up being 1 minus sine squared gamma all over sine gamma. How does this help us? Oh, I know. So you can see that 1 minus sine squared. So I mentioned earlier, if you can find two trig functions that are squared, you want to be on high alert for a Pythagorean identity. But it also works if you have a trig function squared and a 1 involved. So here I have 1 minus sine squared theta. So I have the Pythagorean identity involving sine squared and 1, but this doesn't match with what I have here. So I can manipulate this equation so that I have a 1 minus sine squared theta, and that means I will just subtract sine squared theta from both sides. So cosine squared theta equals 1 minus sine squared theta. So that means I can replace all of this in the top with cosine squared gamma. Oops. And it's still over sine theta. Well, what does this cosine squared mean? I haven't mentioned anything about this, but this means the cosine function is being squared and not the angle gamma. So what that means is that I can rewrite the top again to be something like this: cosine of gamma times cosine of gamma all over sine of gamma. And what are we doing? We're trying to get to cotangent cosine. Oh, look, so I have a cosine. That's right here. And if you look at the cosine over sine, we can rewrite that fraction as cotangent gamma. So one more step would be like this. Cosine gamma over sine gamma times cosine gamma gives you this. So all of this work here is the answer. So the work kind of cycles around this way. So I started here with the reciprocal identity and multiplying both top and bottom here by sine of gamma, so I could combine these terms into one. And then using the Pythagorean identity here to get cosine squared, splitting it apart, writing it like this, and that leads right over into this answer. So you can see this will take a little bit of work to verify these identities, and it's just going to take a lot of practice and a lot of playing around before you will fully 100% understand how to verify. This one I'm going to leave for you to try. We will pick up here in class.